Okay, let's get it started. Do you have any question about this pairwise exchange method or three-way exchange method? There is a cons and pros. This is a really simple one, but you cannot easily apply this pairwise or three-way or four-way exchange model if the target department to be exchanged is not the same. It is very good for the exchange one-to-one, but except that it is not so good. Okay, did I explain about the topological location problem? You know, in 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 the layout, you are supposed to list the number of department. Okay, as the Professor Kwang-Guk Lee presented a couple of weeks ago. You know, there is a department, and you are supposed to explicitly write out how this relationship is, defined. If you don't have the quantitative information such as Fij, so material flow or flow volume from department I to department J, right? If you have such kind of information, it's a very nice thing to do. But if you don't have it, you can at least build the affinity diagram, which are usually expressed in this triangle. Things like that. It is discussed in Professor Kwang-Guk Lee's presentation. You know, without knowing it, if you have this, then you don't have to do this. But anyway, if you don't have such kind of information, you can qualitatively describe the affinity between department using this one. Well, you can assign 1 to 5 or highly or normally or not. You can use 1 to 5 scale, or I don't know, maybe solid dot, empty dot. You know, as long as you can describe the level of affinity, whatever scale you can use, that doesn't affect at all. But anyway, affinity diagram, basic of affinity diagram like this. If department and department 2 requires very close relationship, then, well, I can assign number 5. If department 3 and 1, I don't know, maybe degree of 3. So by filling each of these empty spaces, you can systematically describe how much affinity, affinity means the level of closeness, how much affinity this department requires for the better layout design. That is the affinity diagram. Well, this is the d-value basic. However, if you actually have this F sub ij matrix or Cij matrix or Dij matrix, you can more easily apply this layout design. Okay, question so far? Okay, thing is like this. If you have the concrete number you can go ahead and use it. But if you don't have that number, you can assume this is the f sub ij, right? Okay, so the overall layout sequence is like this. Based on the input or information out there, you have to collect the required information. And by the way, among them, flow of material is really important information. Also, activity relationship is very important. If some of your factory may requires the closeness heavily dependent on the information flow, then you can add information flow as well. Anyway, in most of the time, based on this flow of material or activity relationship. Okay, let me ask. Everybody are familiar with this flow of material? It's F sub ij, right? How much materials flow from department I to J. What this activity relationship means, I think I explained a couple of days ago. What is activity relationship? Activity is done in the department. What activity? Some manufacturing process. And, I'm not sure, but department 3 should be done. A part should flow from 1, at first from 3, based on its design. Like plate cutting should be done before it is welded together and assembled and the like. So by the product design, we know the activity relationship. Something should be done before the other thing, right? Yeah, that's an activity relationship. And this activity relationship are usually come from the product breakdown structure and other related information, right? Based on this too, we can draw the relationship diagram. Relationship diagram is something looks like this. Well, if this is department 1, department 2, department 3, department 4, 5, 6, and we can draw things like department 1 and 2 are related. How can we tell two departments are related or not? Based on the activity relationship and flow of material. Okay, to make the things simpler, let's only focus on the flow of material. If a material flow from department I and J, then I and J are related, like this. For some two departments, it may not be related at all. So, for example, this kind of diagram we can draw. This is relationship diagram. Okay? And the next step to do is space requirement. But while determining this space requirement, we have to think about the current state. Right? Okay. Let's take some example. Let's assume that the department number 1 is sandblasting department. At the earlier stages of ship production, at the stockyard, steel plates are just stored there, delivered there, and when the steel plate to be used, it is picked up by the crane and it's located on the conveyor belt, which is related to some sandblasting and or maybe surface preparation workstation. In that machine, small steel balls are blasted by pressurized air, and it cleans up any dirty material such as rust or dust and the like. It cleans up, and after that, the primer, the basic paintings are applied to the cleaned surfaces, and it is cured. Some heat is applied to dry up. That is what we call is surface preparation. According, there may be some other type of surface preparation. Heating is first applied and then shot blasted, or But anyway, basically, preparing the raw material, the clean, unrusted, clean painted plate is the job of the surface preparation department. And let's assume you're dealing with the surface preparation. And we know the material flow. Steel plate comes from the stockyard to me, and it goes to other fabrication shop in most of the time. We know the flow of material, and we know the throughput, how much when you design a factory, right? Then you can calculate the space requirement. In order to process the required volume for a given time, you can actually deduce what kind of equipment do you need, and those kind of equipment has its own dimension, and based on that information, you can determine the space requirement of that department. Any question? Okay, basic flow is like this. You're designing a factory, and before starting the designing layout design, you first got to know what kind of product you are producing. In our case, a ship. But that's not enough. You have to be very specific about what you produce. It's a I don't know, maybe 5,000 TEU container ship, and we are producing 10 container ship per year or something like that. And it is highly recommended that you have as much information as you can. So if you have the drawings of your product, it's the best. Okay? So based on that product design, you know how to divide those products into blocks and how much steel you have to produce, how much steel you have to process in your factory's surface preparation shop. So all this kind of throughput information should come from your product information. Also, activity relationship, of course. Flow material, of course. Based on this product information, those two things should be determined. Okay? Question? Okay. Then you can draw the relationship diagram like this. And for each department, you can deduce the space requirement. Okay, question. Your factory consists of 6 different departments, and you follow this step and calculated the required spaces, and you added them up. But those required spaces sometimes, and in most of times, are greater than your available space. What would you do? You understand my question? Yeah. Based on your calculation, you require 10,200 square meter, but your available space is only 1,000 square meters. What would you do? You have to adjust. In calculating space requirement, every department manager wants to add some kind of buffer, so have to, divide them up. If we have to reduce 200 square meter out of 6 departments, you can evenly distribute those kind of reduction. But sometimes some department cannot reduce at the same way as the other department can reduce their own required space. Then anyway, you need some kind of massage and discussion between this department. Anyway, important thing is have to think of the space requirement when you think of space. You have to think of the available space when you think of this space requirement. Also, that's not enough. The summation of all the department's space requirement, you can make some number, 1,200 square meter, and your available space is 1,000 square meter. Well, so is it okay to just reduce 200 square meter? That is normally not the case. Have to think of some kind of common spaces. You have to think of the main access road, which will consume the space, right? So your really available spaces only for the department may be 900 square meter or so. But when you think of this thing, do not forget the access road or any other common spaces such as a parking lot and, toilet and, rooms for the stairs and doors, some lobbies and other common spaces. Have to think about it. Okay, question so far? Okay. Next thing is you have to improve this relationship diagram into space relationship diagram. It's just the extension of relationship with the additional information of the space. For example, if the department number 1 requires 200 square meter, then you make this department number 1 big enough to represent 200, and if department number 2 requires only 50, then the scale should be correct, quarter of thing, and it would be nice to write down the required spaces under the name. Any question about space relationship diagram? The next step would be the design stage. You are supposed to design an alternative layout. But while developing this design layout alternative, you have to think about many other things. There will be many other constraints. Practical limitations and other things. For example, department number 1. This is real problem, and department number 1 sometimes should be square by their some practical limitation. It cannot be rectangle. It has to be square. Or some other department, it has to be L-shaped something. Or it has to be T-shaped something. Or it has to be circular. And there are many other practical limitations like this. Okay? Have to think about this to transform this into your first initial design, right? Once the design is done, based on if this is your available landscape, all you have to do is to squeeze this thing into this, right? Once this thing is done, you're not going to squeeze this thing in as it is. Have to think about some should be the, rectangular T-shape, or have to think about it. There is no automatic algorithm to do that. But there are many other things, many other methods to apply this. And then final thing is evaluate it. This is exactly same as you did in the pairwise exchange model. You have to first calculate the cost of the layout by summarizing this. Once you have the layout, you automatically know D sub ij, right? And from here, you already know F sub ij. And from this and from other information, you can know the C sub ij. And by calculating this, you know the cost of this. Okay, if this is not satisfactory, all you have to do is massaging it, iterate these two phases, because those ones are not usually affected by the layout itself. Okay, any question about this step? In the this step is what they call systematic layout procedure. Systematic layout procedure. Okay, I just briefly reviewed the overall procedure, and let's tackle one by one in more detailed manner. Before going that, any question? Okay, it should be very clear on your mind, because on next Monday, your team project will be based on this procedure. So, okay? Okay. Well, in affinity diagram, there are many scales, as I briefly mentioned, and as the Professor Lee mentioned, there are many scales, but usually it's A means absolutely necessary. It has to be adjacent to each other. Absolutely necessary. The next scale is E, especially important. The next one is I, which stands for important. And the next is O, which means ordinary closeness. Okay. Next one is U, unimportant. And the final thing is X, which means undesirable. Okay, and in real application, well, this kind of thing should be determined in team meeting of the layout design team, and maybe cross-functional team will be required. You know, general manager don't know about the specific requirement of each workstation, so one representative from each department can participate this kind of meeting, and this is really important. And if so, for example, with department 1 and N requires important adjacency, then we can mark like this, or you can mark 7, 5, 3, or anyway, scale is not important, but has to be very consistent about it. This is really important. And in more expanded way, they tends to write some kind of number down here, which specify this scale only represents the level of closeness, but sometimes it is not enough. The type of closeness can be sometimes very important. So another code can be applied. Example is like this. there is another code. Code 1. Same doc. Or, you know what the doc means? It's for general manufacturing, but you know, if this is some. Okay, let me explain in this way. In a shipyard, some department, they could be very close to each other, but sometimes it can be laid out into different shop, which is sometimes bad, right? You can specify the type of the closeness like that. Code number 1 should be in the same group, or should be in the same floor. You know, distance from this one and the room right over it is very close to compare to the distance from here to the restroom there. But if it is involved with the moving of the heavy material, this one is not so good compared to this one, right? So number 2, same floor. Number 3, you know, you can specify the type of the closeness in addition to this level of affinity. Okay? The type could be anything. For example, as I mentioned, a floor type, a lane, or something like that. Or the reason why do we require the importance of affinity between 1 and n? Is it because material flow? So we can specify number 1 is material flow, number 2 is information flow, number 3 is the toxic material, number 4 is the sanitary problem, and the like, and the like, and the like. Okay? Important thing is have to be consistent. Okay? By putting more information inside of this affinity diagram, we are trying to give more advanced level of information to the layout designer. Any question about this affinity active affinity diagram? Okay. Okay. Next step is relationship diagram. You know, this relationship diagram could be very complex, and you know, the best possible thing is lay out it at the first stage very nicely. And the thing is like this, you know, have you ever used Microsoft Visio? Oh. Sometimes this relationship diagram could be quite messy, right? Like this. If you start from department number 1 first, which is very, very messy, which is not so good, right? Why do you think this kind of relationship diagram is not so good? Hard to what? Compare. Hard to compare, right? It needs to be easy. Yeah, that's one thing. And the other thing is, this is the topology of your department layout. Topology, which means I am in front of you guys. Amid is to the right side of the Mohammed. Those right side in front of, this is the topology in this layout, right? Location relationship. Those location relationships are determined in this level, right? So, for example, you did this, and as I mentioned, based on this space requirement, your next step will be space relationship diagram construction. So you will make the department bigger by according to their space requirement. And if it's not clearly done here, you cannot make nice layout, because those line means the affinity, right? If this department is too large, those line could be easily blocked. Crossload is not a good thing in factory. You have to wait for some other material to pass, which is bad. How can you make the material flow done in most of time uninterrupted? That is defined in these stages. Okay, the rule is like this. It could be done automatically. However, if you are familiar with some diagramming tools such as Microsoft Visio, you usually draw many organization chart, object-oriented chart, and when it becomes very, very messy, they have a layout button. When you just click it, they just automatically rearrange things to prevent those cross line. Okay? Not making a cross line is really important. Rule of thumb is like this. First, you have to start with the department with many spokes, which means let's think about this one. 1, 2, 3, 4, 5. We have 5 departments, and it is always very nice to start with department with largest number of spokes, the relationship, and start with it and put it in the center. Okay? And located the next department, which are related to the first department, but the next largest number of spoke. And you keep going and going and going. You can, in most of the time, can make this kind of uncrossed layout of relationship diagram. Question? Okay. I'd like to ask you to do some sample problem. Okay. There is a 5 department. Okay. Let's assume these are the level of required closeness. 0 is the lowest, require nothing. 20 is the highest. Can you draw the relationship diagram? Let's take a 10-minute break at this point and keep doing the example during the break time. Okay? Okay, completed. You know, there is no right or wrong answers in this kind of example. But rule of thumb is, as I mentioned, you have to first start with the largest department with the largest spoke. But let's look at this affinity diagram, or sometimes activity diagram. Department 1 has something to do with other department, except that. So spoke is 3. 2, 3. 4, 3. 5, 3. 3, 2. So number of spoke, maximum number of spoke is 3, right? And the department with that maximum number of spoke is number 1 and 2 and 4. So we know that anyway we have to start with department 1 to 4 in any way. Any question? Yep.
So why is it department number 3 has 3 spoke?
3 has 2 information, 2 spoke.
But this is
oh, sorry. 1, 2, 3. 3, right?
So we have to take account of all the parts.
Okay.
So different 4.
Right. 1, 2, 3, 4. 1, 2, 3, 4. Sorry. So 2 and 1 has 1, 2, 3. 2 has 1, 2, 3, 4. 3 has 1, 2, 3. 4 has 1, 2, 3, 4. So 2 and 4. Right? Thank you. Well, if the department with the largest number of spoke is only 1, then we can easily start with that. Okay? Without any hesitation. But now we have the multiple one. Then, what would you do?
Then we will calculate the weightage.
Exactly. The weight. Have to think about the weight. The weight means for department number 2, it has 4 spoke. And let's add up those 4 numbers. And it would be 9 plus 12 plus 13 plus 7, which is 41. How about department number 4? It's a 2 plus 20 and 45. Okay. It looks like department number 4 is a little bit more important than department number 2. So let's put department number 4 here. Okay? And if you look at it, fortunately, department number 2 are related to department number 4. And it has the same number of spoke and almost same importance. So let's put number 2 somewhere here. And it has a relationship like this. 4 and 2. The importance is 13. Right? Yep. Okay. The next thing is 1 has 3 spoke, 3 has 3 spoke, 5 has 2 spoke. So have to think about department number 1 and 3. Okay, we have to apply the same approach. What would be number if you add them up? 27. How about department number 3? It's a 20 times 40. Right? Okay. So it looks like the next will be department number 3. Okay? Then have to think about what is the right location for department number 3. Here, here, or here and here. Well, have to think about the department number 3's relationship with already located department. Department number 3 has relationship with 2 and 4. So with 4 it has 20, highest number. With 2 it's a 12. So we are dealing with the 3. So it's a kind of symmetric here and there, but I'd like to put the department number 3 somewhere around here because it has weight of 20 and weight of 12, right? Yep.
So, the length of the nodes, do they represent the weightage always?
Not really.
Then so why we have putting different 3 closer to different 4?
I will explain. The best possible thing is the weight is related to this weight. If the highest weight the length is smaller, it's a perfect weight. But while doing the layouting, you cannot follow in every time. That's why I say, if you can keep that rule, it's a perfect layout. But sometimes it's impossible because many other things. Okay, we do. So next one is number 1. 1 has relationship with 2, 9, with 3, 8, 4, 10. So it has a relationship with 2, 3, 4, 2, 3, 4, and it should be closest to 4, and then 2. And then 2 and 3. So I don't know, maybe somewhere around here.
So why aren't we placing different one in middle of the nodes?
Middle of all the nodes?
Yes. So
that's possible. Yep.
Then so over no crossing. So there will be no crossing.
Okay, good. Okay. Right? 1, 2, 2, 9, 9, 10, 8. Okay. Which is just like you questioned, if it's going to be perfect one, 20 should be the shortest one, but which is not in this case. Okay, could be, but sometimes it's really, really hard to make everyone satisfied. Okay, that's one thing. How about this? It could be another alternative, or okay, question, is this one the same as this one? Different. Why?
Because in this way, the path covered is much bigger.
Okay. This diagram, what really matters is topology, I said. And in that case, topology means, yeah. Because of that, it's the same. We are only dealing with the topology. Which one is left side of which one is the north side of which, that's all. Okay? So, but this one is this one, in topological sense, different. Right? Do you know what I mean? Okay. Could be a different one. And the next one is number 5. 2 and 7 with 4 and 2. 4 and 2. So it could be inside of it or outside of it. So there are many other possibilities. Okay? Question? Since there are many possibilities, it has 4 and 2. Could be here, could be here, could be here, or since there are many other possibilities, think of the real cases. We are dealing with only 5 number of different departments, but in real cases, the number should be 20 or 30 or something like that. And as the number of department is growing, then the possible alternatives also grows. So it could be many other possibilities out there. Even we are dealing with the topology level as well. Okay? So, if there are not a unique solution, is this wrong compared to this? No, there is no wrong and right answer. This satisfies that. This satisfies that. The level of satisfaction may be different. Since the case is like this, we are using optimization technique to find the optimal thing out of this. Yep.
So shouldn't we be considering that the number of crossing the lines should be kept minimum, right?
Possible.
Yes. So in the second picture, the right one, where will you actually place DPS? Where will you actually place department 5? Because in this picture, the number of crossing is much greater than the left picture.
Okay, that is one nice observation. However, topologically, if you see many crossings, then you cannot satisfy us at all. But based on this, after the space requirement, we want to make this department grows. Starts from this original location. So, if the 4 and 2, number 13, it may be absolutely necessary kind of relationship. So, for given space, we can make 4 and 2 like this, and 3, 1 here, number 5 here, or something like that. Actually, make the design alternative, we can satisfy everything without any problems when there is a couple of, the minima, less number of crossings. But it's very important. Number 4 and 2 requires absolutely necessary affinity. At the same time, 1 and 3 requires absolutely necessary affinity. Then crossing may cause problem. Okay, you know what I mean? Absolutely necessary affinity means have to share some length of edges together. But you cannot make both things at the same time. Logically, we can make things like this to make everyone satisfied, but it's not real case in the thing. Even though we want to make the door, we have to at least have 1 or 2 meters of the width. So this thing is no, but can be done if some is, this relationship requires A level, but this requires the lesser level of affinity, then there is no problem at all. But if these crossings are congested in some area, which is bad. But anyway, in this level, important thing is the topology. 4 is south side of number 3. And, such kind of information, that is really, really important. Okay. Question?
When we make the relation diagram of the team activity, which point is important to decide the weight?
Weight?
Yeah.
So
for example, cost and
basically this. If we want to go more into the how much number we should assign here, then we need some kind of quantitative analysis tool. For example, Fij. From department 1 and 2, the level of flow, I don't know maybe, but in every week, 100 tons of steel are flowing from department 1 and 2. So let's make it's 100. From 1 and 3, it's 200. You can do like this. Important thing is have to be consistent. Okay? Okay. By cleverly building this relationship diagram, we can minimize the number of crossings. Okay? But minimize the number of crossings can sometimes increase the distance between the department. So have to be very careful about it. Okay, building a relationship diagram, I think everybody's understand how we can do it. Even though the number of department is 20 or something, you can do by your hands. Okay, there are many other tools to do that, and there are many other algorithm can do that. And I think you can make computer software to automatically do the relationship diagram layout. You know, select one with largest number of spoke. If there are many departments with same number of spoke, you have to first calculate the weight and do the layout here and there, trying to find the optimal location of the next possible department. Okay? Can you do that? No idea how to do that? Okay. There is an algorithm, and I will explain it on your team project problem sheet. Actually, the procedure I introduced here is not the only way to do this. There are many other approaches, and I choose this because it's a more straightforward. But there are many others, which is described like step 1, do something, step 2, do something, to step 3, do something like this. And I think you guys can easily understand these steps. So if you follow this step, you can do this. Okay? About space requirement, it is kind of domain specific knowledge. Domain specific. The general layout designer cannot determine this requirement. I mean, in order to determine the surface preparation department's space requirement, we have to talk with surface preparation expert. What kind of equipment out there, and based on their experiences and other things, we have to clearly determine the space requirement. Also, it's very specific in shipbuilding industry. Because the product, intermediate product, is really, really huge, we have to think of the size of the intermediate product. You know, there is no way to produce a block of size of 20 by 20 by 20 in this room. Department is so small, so have to think about those kind of intermediate product size, and in order to make the required throughput, you know, we need some kind of specific equipment, and those equipment has their space requirement, and in order to operate that kind of operation equipment, some number of workers are required, and in order to make these workers work in this department, we need some more spaces. For example, restroom, parking lot, or locker room, or something like that. They are, you know what I mean. Some auxiliary spaces, and they are access road and the like. You have to summarize all this kind of space requirement. By the way, question about this? Okay. You know, let's assume we are determining space requirement for the assembly shop of flat panel. And you have the right your product, the panel's width is around 10 meters and length is also 10 meter, height is around 2 meter, and you are supposed to make this thing based on your product mix. You're supposed to make this thing 1 block per week, and you listed up all the required equipment and number of workers, and you all have to think about the buffer size as well. For example, in order to meet the requirement, throughput requirement, sometimes you should have 3 blocks at the same time. You know, you remember those diagram when we talk about just in time or something. Because of that, the number of buffer inventory, sometimes it could not be 0 or 1. It could be some number. Think of the cycle time and other thing. Okay, let me give you an example. To make a to do the process on the flat panel, you need 4 weeks. But your customer, the next workstation, requires one piece, one panel per every week. Then, at least you have to have 4 work pieces at the same time, right? Like this, right? Because cycle time is 1 week, lead time is 1 month, 4 weeks. Because of that, and because the intermediate product is really huge, 10 by 10 by the projected area, we need 4 times of this 10 by 10 in your department to meet the demand. Okay? By calculating like this, you have to determine the space requirement. And there is no clear rules or algorithm or any other things to automatically calculate this space requirement. It has to be done one by one, manually, discussing with your co-workers and other things. Okay, question about this? Okay, next step, space relationship diagram. Let's assume space requirement is done. How can you implement this space relationship diagram from this? Easy. You just make things larger according to the space requirement. Okay? You can make it circular or you can make it rectangular, whatever you want. However, have to always think about this one. You know, there are many practical things like this. If this distance is like this, but the space requirement of the number 1 is much more larger than that, you can end up 1 is big enough like this and 4 around here, which practically impossible. If that's the case, you have to go back to the relationship chart and do the things again. Okay? But other than that, you can explode it because the most important information is topology from this diagram. Which one is left to which one is the south to which, that's the important thing. And make things accordingly larger and make the distance accordingly to the scale, and that's it. Once you make it, then this is really important thing. Number 6. From this space space relationship diagram, and now you have to think of your given length shape. Now you have to do the real designing. There are many other approaches, but simplest thing is this: make grid. Fine enough, but don't have to be too fine. And the way is this. You translate number of cells into space requirement. For example, this number 4 requires 200 square meters, but based on this grid, the 200 square meter equals to 20 cells. Other thing, 15 cells, 30 cells, and the like. And the next thing is, you put this diagram right on this grid, and you just begin to mark the required number of cells. That's it. But there are many practical limitations, such as this department should be rectangular shape, or this should be, it could be rectangular shape, but the shortest width should be greater than some length, or there are many other practical consideration. Have to think about it. So there is no clear and straightforward way to do that. But people do this. Okay? Well, with five departments, we can manually do it. But if the number increase, and for example, I once participated in some ship initial layout program, and it requires arrangement of about 20 spaces into here, so it is virtually impossible. So I use some kind of artificial intelligence technique to automatically do that. But anyway, there are numerous other ways, and if you're interested, you can make your own way. It could be your very nice master's thesis. Okay? You can use artificial intelligence, you can use fuzzy theory, you can use swarm optimization to mimic the behavior of the ants or bees or something like that, or you can use purely mathematical optimization technique and the like. Question? But anything could be eventually evaluated. Question? Oh. Okay. In your term project, how would you transform this one into this? Well, there could be many other possibilities, but I would like to suggest some kind of programming, which is basically the basics of artificial intelligence. And I want you to make things locate initially here and make things grow until, based on the space requirement, this one has to be grow until the cells should be 20. This one should grow until the cells is 15 or something like that. So it can grow north, south, east, west, right? Not one by one. Once it grows, not at the same time. It grows to north, now it becomes here. And now it becomes to grow this direction, it can be here. Now grow to this direction, it could be this. This direction, now it could be 3. Algorithm can be different, but it can keep growing until it meets another competitor. For example, this one has grown to this, and now it wants to grow with this, but this one grows to this. Then you need some kind of conflict resolution algorithm. Which one do you want to do? Well, it depends on the summation of weights. If it has the higher weights, the department has the higher weights. According to that weight, you can give the priority or something like that. But anyway, basically, you can program the growing algorithm based on this. In real life growing algorithm, it's much more complex than this, based on the shape and the access distance and other things. But that's out of the scope of this project, these courses. So, but okay, you guys looks unhappy. Are you familiar with the programming? MATLAB or C++? Okay. Can you do the graphic programming? If you can show these things growing in real time, it would be best. You can make a grid, and you can just turn the changes, the colors in real time, which will make this kind of growing things. What do you think? Can you do that? Have you ever performed the visual C++ programming? No? How about MATLAB with graphic user interface? No? Okay. Okay, I will think it over for this weekend, and there must be some way to do that. Okay, thank you.